This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. Hope you had a very good Easter break. Yeah, my break was not good. You can see I got fever. So today we will be starting a new section, that is cascade stages and current mirrors. So now we studied BJTs, MOS. Now we are going to study cascade stages and current mirrors. Then before that we will go back to our aim, why we want to study this section. When I started the lectures, I took 741 op-amp as an example. What we are trying to do is we are going to study the internal block level diagram of this operation amplifier. So this is operation amplifier. Inside the operation amplifier, or if you want to design an operation amplifier, you need to make current mirrors, you need to have differential amplifier, that is the input. Then you need to have voltage level shifter, output stage, gain stages, and even some capacitor here. This is for making some filter. So we should know all these things, then only we can design an operation amplifier. So once we study the internal block level diagram, we will be pretty much covering all the major concepts in the analog electronics. So that's the beauty of operation amplifier, the internal structure. The internal structure has all the concepts, all the major concepts in the analog electronics. So now you are familiar with the gain stages. Like when you design an operation amplifier, you don't need to design like this. This may be a bit complex design. You can design a simple one. Maybe we will kind of design a simple one towards the end of your lecture. By that time, you also will advance in your labs. So gain stages now you are familiar because you know how to design a simple amplifier or a single stage or a multi-stage amplifier. Then now what we are going to study is a current mirror. So you can see in the operation amplifier, here there is a block that is a current mirror. Here there is another block called a current mirror. Again here there are three blocks in the operation amplifier with the current mirrors as the block. See, three blocks. So these current mirrors are very important. So we will study current mirrors, but then before studying current mirrors, we will be studying cascade stages. Then we will study current mirrors. So that is the reason the heading is cascade stages and current mirrors, because without understanding cascade stages, we will not be able to study current mirrors properly. So that's the reason we are studying cascade stages and current mirrors now. So before that, current sources, we already studied current source because that is the starting point. So what is a current source? So when we have a simple resistor and then you have a voltage supply VCC and then you connect it to a ground. So maybe this is a battery, you got a resistor, then you connect it to a ground. So the current passing through this resistor is depending upon the value of the resistance. That is a IC. So you vary the VCC, and then what will happen is when your VCC is increasing, the current will increase. So that is the reason you get a straight line, Ohm's law. And then when you take the slope of this one, then you get the value of resistance. But if you connect a current source, I am talking about ideal current source, because this notation is used for ideal current source. So if you connect a current source here, what will happen is you keep increasing your voltage, but then your current will be constant, because this current source will make sure that this current is constant. Then who will decide the value? So when you design this current source, you can decide some value, maybe 1 milliamps. If you put 1 milliamps here, no matter you increase your VCC, you increase or decrease, this current will be 1 milliamps, means flowing through this one. You can also vary resistance. Still this current source will make sure that only 1 milliamps will go through. So that is an application of a current source. So current source is used in different applications. As I mentioned, when you have a laser diode, you can use a current source. In the CMOS chip, current source is used for biasing. We will come to that point, biasing, because we have seen the load resistance we replace with transistors, and then some of them are current sources. So to start with, you can see when you connect a current source, it will keep the current constant. Then how to realize a current source? So in order to realize a current source, we can use a transistor as a current source. When you use a transistor as a current source, what you need is you want to keep the current constant. So you can connect a fixed voltage, because if you connect a fixed voltage VB, then your current will be constant. So even MOS, you can use the same, because when you for the MOS, when you draw the small signal, because this is a constant DC voltage, so you will be grounding, and then this part is anyway grounded, and then GMVB, that is a current source. Again, we are taking the ideal case, no channel length modulation or no early effect. So then you can see X point here, and then this ground between, you can see a current source. This is a voltage dependent current source, but then if you are connecting a constant voltage, then this current will be constant. But then when you operate MOS or BJT as a current source, you have a problem compared to ideal current source. So this is ideal current source. This one will operate only after this region, means saturation region. If you are using MOS, it will act as a current source only from this point onwards, not in the saturation region. So then if you are operating in this region, then you can use your transistor as a current source. This region, you have to bias it. So when you talk about a current source, see, this current source I represented here as X and then here as ground. So that is the reason X, and then this is the current source notation, and then ground. Then there is also another current source that we can get using a PMOS, because this is using NMOS, this is using PMOS. When you are using PMOS, the biasing is different, as you know. So we will be connecting source to the VDD, and then this is a point Y. So the difference is here you can see, as I mentioned, NMOS, the direction of the current. So the direction of the current is the direction of the arrow. See, this arrow is coming out, means current is flowing from X and then coming down, and then it is going to the source, from the drain to the source. See, arrow. So that is the reason this current source from X, the arrow is pointing down. See, this arrow. But for PMOS, you can see the arrow is same. See, coming from here, arrow is pointing here, and then it is coming to Y, and then VDD, it is starting from VDD, but then this is starting from X to the ground. See, X, a point X to the ground, but when it is PMOS, it is from VDD, and then the current source, this is the direction, and then it is coming to the point Y. So then my question is, so these both are current sources, but then what is the difference between this current source and then this current source? One is starting from X to the ground, another from VDD to the Y. So what is the difference? Any difference apart from the drawing? So here I said here connection must be to the drain to act as a current source, because that is the structure of the transistor. So you have to make sure that you should be connecting your drain to act as a current source. Means here you might be connecting some device where you want to keep the current constant. Here you will be connecting a device where your current will be constant. So this is a hint. So I am going to connect this here, a simple example. I am going to connect here a laser diode. Here I am going to connect a laser diode. And then maybe another point I am connecting to VDD or something. Then what will happen? Maybe I can draw it. So somebody decided to use a transistor as a current source, and then which makes sense, because when you plot IC versus VC or ID versus VDS for MOS, you will be getting something like this. And then you can see here the current is constant after this region. For MOS, saturation region; for BJT, active region. So this region is a very good region to act as a current source. But then the question is, you have got NPN, PNP, NMOS, PMOS. So if you take NMOS, then what you see is, this is one design. That's what we saw. Here we are connecting a constant DC voltage, VB, NMOS. and then this we represented like this. Another one is PMOS. So when you draw PMOS, so you can see here the arrow is here, and then here you got VDD, and then this is a Y, same BB, but then this we will be representing VDD to a point Y. Then my question is, suppose we are connecting, nobody will connect like this because this is just for understanding, because people will be using more sophisticated circuit when you are using current source. So nobody will use these type of connections, but still this is for just understanding. So you are connecting a laser diode here, LD, with this one. So this is your point X, and then this is your VB, and then this is and the laser diode did 1 milliamps. So then you connected VB, the voltage you varied accordingly to get 1 milliamps. So here you connect your VDD. Then you are getting 1 milliamps. Then this is a point X. Then here, if you are using PMOS, then if you are using PMOS, what will happen? Then you are getting here the Y, then you got VDD, again you are getting VB, maybe VB equal to X millivolt, or volt is good, X volt, same, X volt, which will give 1 milliamps, that is our requirement. So here then I will be connecting laser diode, that's 1 milliamps requirement, we bias, same voltage. Then this I am connecting to ground. So this is a point Y. So then what is the difference here? So as far as a laser diode is concerned, if you check it, what is happening here is this current source, that is pulling the current, maybe that is the first word, current from the laser diode. It is taking the current from the laser diode and sinking to the ground. See, that is the reason this representation. So this current source can take current from a point and then it will sink it to the ground. See, but then this one, here what is happening is this current source can take current from VDD and then this can pump the current. This point actually you are getting lots of current is coming. But then from here, this is taking away the current. You know what I meant? So if you, here from this point what is happening is this current source is taking all the current from this point, then going to the ground. So this is a sink point. From here current is taking, the current source is taking current from this point and bringing to the ground. But this one, what is happening is this point, the current source is bringing current to this point. You know what I meant? There are two things. So that's the reason here this laser diode will feel that it is taking the current. This current source is taking the current. But then here what is happening is it is pumping the current to the current source. It's a laser diode. This current source is pumping the current to the laser diode. So that's the reason there are two types of current sources. One is you can act as a source or a sink. So this is a source and then this is a sink. So these are the two types of designs. So that is a difference. NMOS draws current from a point. See, it is drawing current from a point. Look at the arrow. It is drawing current from a point and then sinking to the ground. So sinks current. So that is the reason it is sinking the current from a point to the ground. Where PMOS draws current from VDD supply to a point. So it is sourcing the current. Means if you touch here an ideal situation, if you touch here, what will happen? You feel lots of current coming. But then if you touch here, what will happen? It will draw current from your point, your hand. It will try to take more current. It is like you got, the best example is maybe this is the following. You got a vacuum pump. In the vacuum pump, you can vary the rotation. So in one direction, clockwise, when the vacuum pump is rotating, what will happen? Then you put your finger, it will suck your finger in. Okay, so that is what is happening. From X point, it is going to the ground. But then you rotate the pump anti-clockwise, then it will push away your finger. Means the airflow is different. So same way the current. So here the current is going to the ground, here the current is loads coming to this point Y. So that's the reason it is a sourcing current, and then this is sinking current, this is sourcing current. So that is the difference. Then you will understand when we design current source later. So this much understanding may be enough. So this one, NMOS, means it can draw current from a point and then it can go to the ground, sink it. PMOS means it can draw current from a VDD and then it can source it to a point Y. Not really. You can design using both the ways. But then there are some cases where you need the sourcing. For the laser diode example, you can connect in whichever way we wanted. Then ideal current source, as I said, it got infinite impedance. So ideal current source, IV characteristics. So when we talk about ideal current source, then we got this, suppose we got this RC here. Then this is a collector current. So this is a simple amplifier configuration. And then here you can see your RC will decide whether this amplifier is in the saturation or active region. Because once you increase RC, what will happen is this transistor will go to saturation, which we already studied. Then your gain equal to minus GM into RC. So if you want to increase the gain for a given bias, we have to increase RC. But when we increase RC, what will happen? If you increase RC beyond this point, what will happen if you increase RC? Definitely the transistor will go to saturation. Then somebody will ask you a question. Is there any way we can get rid of this one? Is there any way we can get rid of this effect? Can we connect something else here which should give same current, but then it should not affect the bias current, but then you should have a very high RC. So you can use a current source. So if you use a current source, then the advantage is here, if you are connecting a current source, if you are connecting an ideal current source, you can set this current IC, but then the ideal current source got a very high input impedance. You know what I meant? So I can draw it. So when you have an amplifier, so this is your RC, this is your V out. This is a simple amplifier. And then your gain equal to minus GM into RC. So if you try to increase the RC, what will happen is, RC when you increases, this voltage will drop because your VCC equal to, so this is the current IC. IC, RC plus VCE. So when you RC your increases, then what will happen is your VC will decrease and then it will go to saturation. But then the question is, can we connect something else here that can increase the gain of your amplifier? So if you can connect a current source here, so if I replace this with a current source, ideal current source, then ideal current source got an infinite impedance actually. But then ideal current source can pass current. It can bias to a particular current, the current of your interest, so that you can get actually a very high gain. So that's the reason the chip design, people will be replacing maybe your load resistor with a current source. Or in your emitter follower, your RE they will replace with a current source. Then the advantage of current source is not only getting a very high impedance, but you can also keep this current constant. Your bias current will keep it constant. Current source, if you put current source, if you use current source and keep this current IC some value X milliamps, it will keep that X milliamps, your DC current. So that's the reason current source is important. But then when you use a current source, as I mentioned here, so you said, okay, this is a very good idea, I am going to implement it. So when you implement it, you have a problem. The first problem is you don't have an ideal current source. All the current sources got some impedance. And then as a beginner, somebody will ask you, design one current source for this particular amplifier application. Then what will you do? then you can design. So you will say that, okay, I got some experience. So this is your circuit. So this is your VCC, and then this is a current source. And then you can say that this is your current source, and then this is pumping IC. And then you can design this current source using a transistor. And then when you design your transistor using this transistor, actually what is happening is here. So this part, so you are getting when I draw a small signal, so here you are connecting a constant DC voltage at the input for this transistor, TR. Okay, and then you are getting a current, but you got your RO. This is a point X, this is a point Y. So this is a point X, so this is a point Y. So you got X, Y, you are going to connect it here, X, Y. But then the problem is you got RO. When you got RO, then what will happen is this is equivalent of, you got your amplifier here, this is the input, this is the input, this is the ground, then you got a current source. Now your current source I have to represent like this. You know what I meant? So ideal case, this RO will be infinity. If RO is infinity, that is the ideal case. But in the real world, if you are using a simple transistor as a current source to increase the gain here in the chip, then your impedance of the current source is RO. Then if the impedance of the current source is RO means, then your gain you can't increase that much. If you got RO here, then that will definitely decrease the gain. But still, it is much better than using a simple resistor, even one transistor. But then people came up with strategies how to increase the impedance of the current source. So if you can increase the impedance of the current source using some techniques, then that is fantastic. So that our aim is if we can push the impedance of the current source to infinity, a bigger value, then that is actually very good. So our aim is if we can push this RO to infinity, then that is very useful in the amplifier applications, especially in the chip. So that's the first part we are going to study. So that's the reason we are studying cascade stages. There are some techniques where we can use, some we already studied. Now when I pull out that section, what we studied, you will understand, yes, yeah, we studied this part. Actually, you already studied some techniques how to increase the impedance of the current source, which we did not discuss previously. We studied in some other context. Now I will show you how that technique increased the impedance of the current source. So if the current source is not ideal, we will be connecting a resistance in parallel with the current source. So now what our requirement is how to increase the impedance of the current source. So when the current source is not ideal, we will be representing current source, put an R. So this is a non-ideal current source. So non-ideal current source will become ideal when your R tends to infinity. Then somebody will ask, how can you, even this notation we can explain, because when I have this current source, this for just for your understanding, so this is my laser diode, and then this is a VCC maybe equal to 2 volt. I ground it. Okay, so maybe this is an interesting way of explaining. Then here the current is 1 milliamps. This current source I biased in such a way that I get 1 milliamps. Then here what I'm using is I'm using a transistor, and then this is a ground. So this is a point X, this is a ground. So this is a point X, and then here I have connected maybe 0.71 volt. Then I'm getting around 1 milliamps. So this voltage is constant, so this is 1 milliamps, so I am getting 1 milliamps here, and then this I am going to connect it here, then laser diode is biased. And then this is an ideal current source, so your RO equal to infinity. If there is a fluctuation, 2 volt went to 3 volt or came to 1 volt, extreme cases, then what will happen is nothing will happen. This will make sure that, because this bias is constant, so that this will make sure that only 1 milliamps only will flow. And then only 1 milliamps will flow. If your transistor is not ideal, or if you are taking into account the early effect, or if your current source got an impedance, then what will happen is you are connecting an RO here. Then what will happen is when your 2 volt is increasing to 3 volt, then what will happen is your 1 milliamps plus the current might increase by another delta X milliamps. You know what I meant? Then here the current will become 1 milliamps plus delta X milliamps. Then this current source will make sure that only 1 milliamps will go through it. Then the delta X milliamps will go through this RO. You know what I meant? So that's how, if current source is not ideal, this delta X milliamps will go through this RO, so that your current will actually increase a little bit. But if you keep this RO infinity, what will happen is this delta X milliamps will stuck here, it cannot flow through this one. Only 1 milliamps will be flowing. So the circuit will adjust it. So our aim is how to make this RO infinity. So using one simple transistor, if I connect here, this RO is not going to be infinity, it is a finite value. But then we have studied, we can increase the value of RO. Do you remember that? Yeah, add another transistor, or if we connect, instead of this one, you are right, simple connect one RE. Same transistor T1. Here I am going to connect 0.71 volt. Now this is my new one. So if I replace, this is X, this is X1. So if I connect this one here, what will happen? Much better, or because here your impedance is equal to RO. So what is your impedance here? Yeah, here the value is much bigger, not simply RO plus RE. Actually, this is much bigger than 1 plus beta times. So that actually we are increasing the impedance of this current source. So that is one technique. So you can increase the impedance of the current source by using another RE here, which we already studied. When we connect an emitter degeneration, actually we are increasing the value of RO, output impedance. And then that we can use in the current source scenario, so that you can make current source as closer to the ideal value. Or what is another way of explaining is when you have this RO for this particular one, when you take into account RO, your VC versus IC, the characteristics will be like this, and then this slope, that is your RO. That is for this X1. So that is for your X1. But then for X, that is for your X. Sorry, that is for your X. Then for your X1, what will be the slope? It will be smaller, or so this is for your X, this slope. But then this is ideal value. Then for the X1, your slope will be somewhere here. So this is for the X. You know what I meant? We are actually reducing the slope. And then if this RO equal to infinity, what will happen? Then that is a straight line. So that is the reason the current source, we have to reduce the slope. And then that is the reason we have to increase output impedance. So ideal current source is the best. But then we can't get the ideal current source. But then if we can increase the impedance of the current source, then we can replace your load resistor with current source, which got several advantages such as compact design. You can keep your current constant, you can get higher gains. So output impedance of the current source, which we already discussed. If we don't take into account early effect, we will say that okay, this current source got infinite impedance. RO equal to VA by IC, which we already know. RO equal to infinity. If no early effect and for most no channel length modulation, then if you are using one transistor as a current source, you are through. You don't have any issue. But actually, in the real world, you got channel length modulation and early effect. So then what is happening is your RO is finite. Then you are getting a slope here. That is output impedance. So our aim is somehow we have to make it flat, this region. Increase output impedance. So then we know that we can increase it by connecting an RE, which we already studied. Your output impedance, previously it was RO, but when you connect your RE, actually you can increase it. We already derived it in the previous slides. If you want to find out the output impedance, we already derived it. Maybe this is maybe third or fourth times you are seeing this derivation. Because when you want to find out the output impedance, what you do is you short the input and then connect a test voltage source at the output. That is Vx and an Ix current is pumping. This we already derived it. Then we can write down Vx equal to Ix minus Gm into V pi. That is the current flowing through this RO. That is into RO minus V pi. KVL in this direction. So that is a V pi, and then V pi equal to here. If you measure V pi here minus Ix into Re parallel R pi, we did it several times. And then what I want to show is, see, we remember this equation, we derived R out with Re, which is equal to 1 plus Gm into Re parallel R pi into Ro plus Re parallel R pi, which we already derived the equation. See, so here you can see that the output impedance is actually boosted when we connected a Re, emitter degeneration. When Re equal to 0, all this will collapse and then you get only Ro. R out equal to Ro. But then when we connect this Re, actually we are boosting the output impedance. So if you are boosting the output impedance, means then in the current source, what actually we are doing is this slope you are reducing further down and pushing down to the ideal one. So that is a very good when we design the chip, especially the amplifiers. So that's the reason this current source, when you design a current source now, you will not simply use a transistor, rather you will use one Re as well, so that your output impedance is very high. Emitter degeneration boosts the output impedance by a factor of 1 plus Gm into Re parallel R pi. Same with whatever we do with VJT, we can do with MOS. So R out 1, which is equal to 1 plus Gm Re parallel R pi into Ro plus Re parallel R pi, means this R out 1. Then for MOS, what is the difference? Put R pi equal to infinity. Because your R pi equal to infinity, then what you will get is same here, you put R pi equal to infinity. So if this is infinity, this term will stay. This is infinity, this term will stay. So that is equal to R out 2 here, which is equal to 1 plus Gm Rs into Ro plus Rsc. Even for the MOS, the output impedance is boosted when you connect Rs. Same effect. But then we also discussed when we have a Re, again for the chip we will be connecting another transistor instead of Re, because the chip we will not connect a conventional resistor because of the space, and for a given voltage you can't pump more current. There are two reasons. So here we will be using another transistor which we already studied, that is called cascode stages. So now what you are doing is, instead of a Re, you are using another transistor, and then this is your new current source. So your new current source is now made of two transistors, not one. Why we are using two? Because if you are using only one transistor, your output impedance is very small. That will make your current source very real, not ideal, means with less output impedance. But then if you are connecting another transistor here, then you are boosting your output impedance so that you can push your current source to the ideal characteristics, very high output impedance. And then we know that when we connect a transistor here, instead of Re, what will come into effect here? Yeah, Ro2, Ro, because this is Q2, so we use Ro2. So you can, instead of Re, you can substitute Ro2. That's our only difference. Then instead of Re, now what you see is from here you are looking down, because here you have got Gm into V pi, RO, then only you will get RO2 here, because the VB2, this is a constant DC voltage, this is a constant DC voltage. So this is a constant DC voltage, anyway you will be grounding, and then you are getting only the effect of RO. Maybe I'll draw it. See, you got two transistors here. So this is VB1, this is a DC value, constant DC value. Then what you have done is you connected another transistor instead of your RE. So this is also a constant DC, VB2, DC value, then you have grounded. So when you look down, what you have done is you will get this one, this is the Q1, Q2. So the effect is VB1, it is equivalent of connecting RO2. Why? Because when you draw the small signal of this part, this is a constant DC value, so it will be grounded. So here, this for the Q2. Here this is ground. GM2, V2, RO2, and this is a point X. So this is a point X. So you can see here, this is anyway is grounded, so you don't have anything here. So no current is flowing, so that this particle is 0, GM2 into V2, because here there is no voltage. This is grounded, this is grounded. So you got only the effect of RO2, so that is the reason we have written here RO2. So when we are connecting like this, we are getting only the effect of RO2, which we already studied. Then what we have to do is we will be replacing RE with RO2. So then see, replace RE with RO2. So this is the impedance. So now this is a expression for output impedance of a current source with the two stages or a cascade stage. So this is called a bipolar cascade stage, because we are using BJTs, bipolar junction transistor. So this is called a cascade stage. So cascade stage is a current source with improved output impedance. So this is a cascade stage. And then you can further simplify this one. GM RO2 parallel R/1. This value is definitely greater than 1, because 1 plus this value, so that we can ignore this 1. 1 plus a bigger value, so we can ignore this 1. If that is the case, the equation collapses to R out approximately equal to GM1 RO1 RO2 parallel R/1. See, so these are output impedance. And then again, we already solved this one previously, all these equations, simplification. Then output impedance, sometimes we will be using only this expression to simplify it. Obviously, this is a standard expression. Why we are doing is GM1 RO2 parallel R/1. This one is always greater than 1, so you can ignore this 1. Then we can rearrange it, then we get this value. Then we discussed about connecting this RE, and then we replace this RE with a transistor, and then we are increasing the output impedance of the current source. Then the question arises is how much it can enhance. You know what I meant? So we should be able to understand it properly when we see the number. So that is the reason I have got some numbers, some problems. Find output impedance of a current source. So this is a question. If Q1 and Q2 are biased at a collector current of 1 milliamps, so these both are biased for a collector current of 1 milliamps, means here you are connecting a DC voltage, maybe you are connecting some DC voltage X volt, here also you are connecting maybe some X volt, so that 1 milliamps will be flowing through Q1 and then same current is flowing through Q2. And our assumption is both the transistors are identical. Okay, so then Q1 and Q2 are biased at a collector current of 1 milliamps. Determine the output resistance. So you have to find out what is output resistance or output impedance. Assume beta equal to 100, VA equal to 5 volt for both the transistors. What is VA? Yep. So how will you find out RO? So what is the expression for RO? Yep. So GM, we know that GM, what is GM? Transconductance equal to IC by VT. RO, output impedance equal to VA by IC. R pi, which is equal to beta VT by IC. All these we already know the standard expressions. So we can find out R of simple VA by IC. VA is already given, IC is already given. So 5 kilo ohm. So that is the output impedance. So if you got one simple transistor, so this is if Q1 and Q2 are biased at a collector current of 1 milliamps, determine the output resistance or output impedance. So this is for both. So what I am going to do is I am going to find out only for the one. So if I want to find out only for the one, it is easy because for only for the one, GM equal to IC by VT, RO equal to VA by IC, R pi equal to beta VT by IC. So you can find out RO1 equal to VA by IC, which is equal to 5 kilo ohm. So that is for only one transistor. You know what I meant? If you got only one transistor, it is easy to find out output impedance that is equal to 5 kilo ohm. But here the question is, when you have this Q1 and Q2, you got two transistors. Now what is output impedance? But we know the expression, but then how will you find out? R out. So here it is easy, R out equal to RO1. But then here what is the expression for R out? So for single transistor it is 5 kilo ohm. So our question is, now you have to find out this R out for Q1 and Q2. See, I already given you enough clue. For one transistor we already found out 5 kilo ohm. Now the question is, you are going to connect maybe another transistor and asking how much. So we got 5 kilo ohm. For one transistor it is 5 kilo ohm. So if you connect another one, same 5 kilo ohm, how much? 10 kilo ohm. 25. So this is our equation, R out, which is equal to 1 plus GM1 Q1, RO2 parallel R pi 1 into RO1 plus RO2 parallel R pi 1. From where this equation came is from here we are just borrowing this equation. See this equation. So which we already know. Yeah, you make it, so but then we are going to simplify it. GM1 RO2 parallel R pi 1 is greater than 1, so we will write R out equal to GM1 RO1 into RO2 parallel R pi 1. Now how will you find out? R out equal to GM1 RO1, RO2 parallel R pi 1 means RO2 parallel RO2 into R pi 1 but divided by RO2 plus R pi 1. Then you substitute all the values. GM IC1 by VT, GM1, RO1 VA1 by IC1, RO2 VA2 by IC2, R pi 1, what is R pi? Beta VT by IC. So R pi 1 equal to beta VT divided by IC1, RO2 VA2 by IC2, R pi 1 beta VT by IC1. So when you substitute this equation, then you can cancel out some, because you assume your transistors are identical. Then when you substitute the values, you get R out equal to 328.9 kilo ohm. See, if you are using only one transistor if you are making a current source using only one transistor, your output impedance is only 5 kilo ohm. But if you are connecting one more transistor, means using emitter degeneration, you are using two transistors, then you are getting output impedance of 328.9 kilo ohm. So your current source got a very high input impedance. See, so the value you can see 5 kilo ohm and 328 kilo ohm. See, means how much increment? Cascoding has boosted your RO by a factor of 66 times. So that is a kind of boosting bigger value, much bigger value. Using a simple transistor connection, you have boosted 60 to 66 times. So that's the reason cascoding. So cascoding will definitely increase your output impedance of the current source. Yep. And then maybe I'll stop here today. Yeah, just derive it and see whether you are getting these equations. This is very simple substitution.
anything come through?
Yeah, it did. Stuff like that. Where's that?